So good morning to everybody. In this video we are going to see one of the important university question, that is in the fourth unit, that is derivation of single line to ground fault current. So let us go through the video directly.
As we discussed the line to ground fault, so as the alternator is unloaded,
that means before fault, I can consider the IR to be equal to 0. Similarly, IY will be equal to 0 and IB will be equal to 0, right? Again, you can see the voltages here, your VR, VY and VB at the terminals, okay, they will remain balanced before fault. Okay, now after fault, okay, now let me consider the IR phase, okay, R phase is, okay, let me consider this IR line current is shorted or grounded through a fault impedance ZF. Okay, let us consider this fault impedance ZF. Now you may consider this ZF or Zn according to the circumstances you are having. Okay, it may be solidly grounded simply. Here also you can ground it solidly, and here also you can ground it solidly. Okay, so when you ground them solidly, there is no presence of Zn or ZF here. Okay, but I am considering Zn and ZF so that we can have a broader outlook on the equations as well. Okay, so that means here after fault what we see, this IY, here the circuit is open and here IB is open. That means your IY will be equal to 0, again IB will be equal to 0, and your IR is not equal to 0. Okay, so let us consider here the fault current as IF. Okay, so your IR will be equal to IF. Okay, and you can see here, if I say the voltage at this point is VF, so your VF will be simply equal to IF into ZF, right? IF into ZF. Now after fault, this VR, VY and VB gets unbalanced again. Now in our last videos we have seen that the currents IR0, it's a positive zero sequence current in red phase, IR1 positive sequence current, this is IR2. So if you put them in matrix, so we are having 1 by 3 times of, okay, 1 by 3 times of 1 1 1 1 alpha alpha square 1 alpha square alpha, or you can simply write it as A. Okay, let us write it as A. Okay, 1 A square 1 A square A, and here we are having IR, IY and IB. Okay, so this will be the other matrix. Okay, fine. Now in the fault condition, that is line to ground fault, okay, line to ground fault, here we can see IR sorry, that is IY is equal to 0 and IB is equal to 0. So you put this as 0 here, this as 0. Now after doing so, what we get is your IR naught will be equal to 1 by 3 times of IR. Okay, 1 by 3 times of IR. Again your IR1 will be equal to 1 by 3 times of 1 into IR, A into 0, A square into 0. That means here also you will get this IR1 will be equal to 1 by 3 IR. Okay, and similarly your IR2 will be equal to 1 by 3 times of 1 into IR, A square into 0, A into 0. So that means your IR2 is also equal to 1 by 3 times of IR. Okay, now you can see here your IR is equal to IF, right? That means you can put here this as IF. So from here your IF will be equal to 3 times of IR naught, right? 3 times of I R naught. So from here you can see that we have seen Vf will be equal to If is 3 times of I R naught into Zf. Okay, now as you can see here, the positive sequence current, the zero sequence current, the positive sequence current and the negative sequence currents are equal. That means they must be connected in series, right? So let us draw the equivalent circuit for this star connected load which is line to ground. So while considering the per phase equivalent diagram, we know that the I neutral current will be equal to 3 times of I R naught, right? That means only the zero sequence current will be containing in the neutral current. Okay, so that means your neutral current contains only the zero sequence current, and this shows the absence of the positive sequence current and negative sequence current in the neutral. Okay, that means in the neutral the current flowing will be 3 times of I R naught. Okay, so if we start our equivalent diagram from here, from the neutral, so let me say this is your ground. Okay, now from here I am having a impedance, let me say this is Zn, and here the current flowing is 3 times of I R naught, right? Now going forward, okay, as there is no power in this circuit or no current flowing in this circuit, your Ey cannot be considered, okay, and your Eb also cannot be considered as they are open circuited. Okay, so here in the alternator we will be taking in a positive phase sequence your ER is considered, because it will be the rotor will be rotating in the anti-clockwise direction, and in that direction we will be considering the positive sequence EMF. Okay, so that means here we are having the positive sequence EMF, that is ER1. 1 is for positive phase sequence, and above we are having, okay, the sequence impedance in positive phase, that is Z1. Okay, and as the currents in the positive phase sequence, zero phase sequence and negative phase sequence are equal, they must be connected in series. So here we are having the impedance, respective impedance of positive, that is zero sequence phase, and negative sequence phase. Okay, so this will be like this. So this will be simply your Z2 and this will be Z0. Okay, so here the current will be your IR2. Okay, here the current will be IR0. Here the current will be IR1, right? So you can easily find the voltages here. So your VR1 will be equal to ER1 minus IR1 into Z1. This is VR2, this is VR0. Okay, and again we are having here the ZF, and this is grounded here, right? So we know this. Now you can see that the current flowing here in the equivalent circuit is, finally we are having IR0. Okay, but here from the ground you can see the current here, it is 3 times IR0. That means in order to make this current and this current equal, what we do here is I will multiply this Zn 3 times. Okay, so that you will be having the current simply as IR0, right? Okay, so in our last videos we have seen that, so if you multiply this neutral impedance with 3 times, then the current IR0 can be written here. Now again you can see here the current here, it is IR0, right? Okay, but here you can see your IF is given as 3 times of IR0, 3 times of IR0. Now in order to make this 3 times of IR0 to be equivalent to IR0, what we do, it is we multiply the fault impedance again 3 times of ZF. Okay, 3 times of ZF. That means we are shifting this 3 to ZF, and I am writing this simply as IR0 into 3 times of ZF, so that your neutral your fault impedance is multiplied thrice to the initial fault impedance to make the currents equal, so that we are having here IR0 and here also IR0, so that your new impedances will be changing, that is 3 times is multiplied for both the neutral impedance and the fault impedance. Okay, so this is basically the equivalent circuit diagram. Now, by using this equivalent circuit diagram, you can find the fault currents and the short circuit MVA. Now, this can be found in many ways. So, let us consider few ways here. Okay, so initially, if I say your zero sequence current, okay, your zero sequence current IR0 will be simply given by, what is the voltage here we are having? ER1. Okay, so it will be simply ER1, okay, upon the total impedances. So this is a per phase diagram. Please remember, it is a per phase. That means you will be having the per unit value only here. So it will be ER1 upon the impedances we are having Z0 plus Z1 plus Z2 plus 3 times of Zn plus 3 times of Zf. Okay, 3 times of Zf. So this is the equivalent impedance, sequence impedance for positive phase sequence. This is for negative phase sequence, and Z0 plus 3Zn is for neutral sequence impedance, and this is your fault impedance. Okay, so this is your IR0. Now we know that IF is simply given by 3 times of IR0. Okay, so what we do here it is, you just multiply 3 times of this term here, so that you got the fault current, and please remember this is in per unit. Okay, this is in per unit. Now when a value is given in per unit, how will you find the actual value? So your actual value can be found simply by, if I write here, your IF actual or in amperes will be given by IF in per unit into MVA upon, okay, MVA upon root 3 times of line voltage. Okay, so once you find the IF per unit value, okay, you can find the IF actual value by knowing the MVA of the system given and the line voltage. Now if we see the short circuit MVA, let me rub the board. Okay, so here one thing I must say is, so here we can see the
So in this video we saw about the derivation of fault current due to single line to ground fault. This is an important university question. Now in the next video we will be seeing the fault current due to line fault. Another important question we will be seeing. So thanks for watching.